So let's look into key insights of big data architecture. Big data architecture is distributed in nature. It can scale up to even thousands of data and processing nodes. We are showing a Hadoop as an example. The same holds true for other technologies also. In big data architecture, data is partitioned, replicated, and distributed among those thousands of nodes. And because of performance reasons, data is partitioned into two classes: hot data and cold data. Hot data is something which is used frequently, say for analysis or prediction analysis. And cold data is something which is used temporarily or less frequently. As a result, there is a nice feature in big data architecture called auto tiering. What it means exactly is that hot data will be moved to high performance disk drive. On the other hand, cold data will be moved to low performance disk drive to increase the performance. This is a very good feature. However, it has some security implications. For example, at any point of time, you do not know where exactly data resides, in which disk drive the data resides. So we will see some of the security implications in the next few slides. Another big paradigm shift in big data architecture from traditional database architecture is that it is easy to move the code rather than data, which means when programmer writes a computational code and data analytics code, the code exactly runs on the data on the disk drive where the data resides, and gather the result and bring back the result to the respective end user. So this is a paradigm shift feature in big data architecture. Performing computation real time and continuously is the next big trend in big data. Suppose you upload a website, update a website right now, Google can tell you real-time analytics within next 5 minutes. That's called real time. Big data also need to collect data from variety of sources. It may be your social media data, it can be your web data, it can be your GIS, financial information, customer information, travel tickets, usage data, meter metadata, etc., etc., etc. And here we are talking about data not in MBs but GBs and terabytes continuously coming to your big data solution, and that's huge. Another key feature of big data is that it supports ad hoc queries. As an example from traditional database is that what if end user can create SQL queries at their end and are able to submit those SQL queries into web applications directly. They will definitely have more flexibility, more power. On the other hand, there are greater security concerns of having ad hoc queries, and we will see in the next few slides. Another key feature of big data is it has massive parallel and powerful programming framework. For example, if you have 16 terabytes of data, which is not really huge if you look at big data, and the data is divided say into 128 MB chunks, then your program will be divided into 82,000 maps or functions that will run concurrently on those data nodes or processing nodes. So that's called massively parallel computation. Second is the programming framework is powerful, means that you can develop programs say in Java rather than SQL and PL SQL in traditional databases. Hadoop uses, now there are quite a few frameworks available that I will talk about. One is Hadoop. Hadoop uses MapReduce framework, where a program, if you see in the image, where a program gets divided into multiple maps that get executed on respective data nodes, and then finally they are reduced or merged. The results are merged together into a single result set. So that's called MapReduce. Apart from MapReduce, we have another paradigm called topology-based computation, which is used by a real-time analysis big data solution called STORM. STORM utilizes a network or topology of spouts and bolts, where spouts are data sources and bolts are processing nodes. So it utilizes a network of spouts and bolts to do real-time computation. And there are many more which I will not cover in this presentation. Finally, there is no single silver bullet. Hadoop is already unsuitable for many big data problems. For example, real-time analytics. There are many emerging technologies which are coming up. For example, real-time analytics. You can look into Cloud Scale and Storm. For graph computation based problems, you can look into Giraffe and Priggle. For low latency queries, you can look into Camel. So there is a big ecosystem of big data technologies or solutions existing for specific big data problems that you can find on the internet. Okay, so let us look into top 5 security risks. The number 1 security risk in big data is insecure computation. Now, what really it means is that untrusted computation program somehow used by an attacker to submit to your big data solution to extract or churn out sensitive information from data sources to send back the sensitive information back to attacker. So that's what insecure computation is. Not only this, insecure computation, apart from information leak of sensitive information, it can also corrupt your data. So leading to incorrect results in your prediction results or analytical results. It can also perform some kind of denial of service on your big data solution, because as you have seen that big data uses massively parallel programming language. Another critical risk in big data is input validation and filtering. Because the big data need to collect input from variety of sources, therefore it is quite mandatory and quite important to validate the input, which involves making a decision of what kind of data is entrusted and what are the untrusted data sources. It also needs to filter the rogue or malicious data from the good one. Now these two challenges are not new. These two data validation and input validation is not new. It's already there in, the same risk is there in traditional databases. However, in big data, because of huge amount of gigabytes or terabytes of continuous data inflow, makes it extremely difficult to perform input validation data filtering on the fly. Second, signature-based data filtering has limitations. For example, it cannot filter rogue or malicious data that has some behavioral aspect. For example, if a malicious or rogue agent inserts malicious but large data into your data set, it can definitely influence your prediction results. So that's what cannot be filtered by, say, a signature-based data filtering. For that, probably you need to have your own custom algorithm. Next risk is not having granular access control. Big data traditionally were designed for performance and scalability, with having almost no security in mind. On the other hand, traditional databases have very comprehensive table, row, or cell level access control, which are really gone missing in big data solutions. Another problem is that ad hoc queries poses another additional challenge. What if your user retrieves sensitive information using ad hoc queries. Last, access control is disabled by default, even if it is provided by a solution. That's another area of concern in big data solution. For example, NoSQL databases you have depends on access control provided by third-party softwares, but it is actually disabled by default. So you need to enable it explicitly. Next risk in big data is insecure data storage. As the data is stored at thousands of nodes, authentication, authorization, and encryption of data at those nodes is really a challenging work. On top of it, auto-tiering moves cold data to lesser secure medium. What if your cold data is sensitive? Which means a sensitive data is moved to lesser secure medium. Encryption of real-time data can have performance impacts. So even if some solution provide encryption, you may not use it because it may have performance impact. Last, secure communication among nodes, middleware, and end users are disabled by default. So you need to explicitly enable it. Last concern in big data, top 5 concern in big data is privacy concerns in data mining and analytics. Monetization of big data generally involves data mining and analytics, and sharing those monetized results, analytical results, involve multiple challenges. For example, invasion of privacy, invasive marketing, and unintentional disclosure of information. There are quite a few examples in the past of privacy concerns in big data. For example, AOL released anonymized search logs for academic purposes, but users were easily identified by their searches. Netflix faced a similar problem when users of their anonymized data set were identified by correlating their Netflix movie scores with IMDb scores. That's really concerning. So let's look into top 5 best practices that we feel that you should consider while designing a big data solution. Number 1 is secure your computation code, which means implement access control, code signing, dynamic, and perform dynamic analysis of computation code to verify that it's not malicious and it doesn't leak critical information. Second is you need to look into strategy to prevent data in case of untrusted code runs in your big data. That's also very critical. Next, best practice is to implement comprehensive input validation and filtering on possibly all internal or external data sources. You need to also evaluate input validation and filtering features of your big data solution. And one of the key questions that you should ask here is that whether their input validation and filtering can scale up to your data requirements. Another best practice we view is implement granular access control. So you need to review and configure role and privilege metrics of the different kind of users of your big data. The users can be administrator, developers, end users, knowledge workers, etc., etc. You need to review permission to execute ad hoc queries, whether you really require ad hoc queries or what access you should get to ad hoc queries that you need to verify. Finally, you need to enable access control explicitly, because as we see that it is disabled by default. Secure your data storage and computation. Sensitive data should be segregated. Enable data encryption for sensitive data. You need to audit all the administrative access on data nodes. And finally, you need to verify whether you have configured API security of all the components of big data. And finally, you need to review and implement privacy preserving data mining and analytics, which means you need to verify your analytical algorithms that it should not disclose sensitive information. And get your big data implementation pen tested.